Welcome, everybody. Welcome to Science Thursday with Brookhaven Lab. The goal of Science Thursdays is to engage our student and education community in STEM topics by meeting Brookhaven Lab STEM professionals and learn more about their work, their career path that got them to where they are today. At the end of the 45 minutes, we hope that you have heard something that will spark your interest in STEM and perhaps consider a STEM career and come back and be part of the Brookhaven Lab community. Good afternoon. My name is Aleida Perez, and I am from the Office of Educational Programs, and I'm joined by my colleague, Salvador Gonzalez, who will be managing the Q&A portion of today's discussion. Before I introduce today's guest, a few reminders. You're welcome to submit your questions on the Q&A chat or the Q&A section that is at the bottom of your Zoom app. And we will try to get as many questions that we can possibly can today. And if you have any issues or difficulties with the stream or any aspects of the Zoom app, feel free to put send a chat to IT. We are very thankful to have George Canales supporting us today and let him know what the problem you might be having. So today I am joined by Ashley Head. She's a scientist at the Center for Functional Nanomaterials at Brookhaven National Lab. And Ashley will share her work that she does at the CFN and also will discuss her career path with us. So welcome, Ashley. How are you?
I'm doing well, thanks.
It's really a pleasure having you here today. I think when we were having our pre-meetings, it was a great conversation. And so I'm looking forward to sharing so for our students to hear the work that you're doing and the path that you have taken to get there. So how long have you been at BNL? Just curious.
So a little over 4 years.
4 years. So just still a newbie here at BNL.
Yeah, I still feel new.
So you and I were talking. You mentioned to me that you are our cartoon aficionado. Can you tell us a little bit about what does that mean? What are your favorite cartoons to watch?
Yeah, my favorite cartoons. I got to say, I'm a Disney princess fan. I love, and in general, all Disney movies. Yeah, and Masha and the Bear is a pretty fun cartoon. Also, some foreign cartoons.
That's very cool. So you see, folks, we scientists are fun people too, right? We just not spend our time in the lab.
I don't have an Elsa dress yet, but maybe this Halloween.
Very cool, very cool. So Ashley, when I introduced you, we said that you work at the Center for Functional Nanomaterials. And so for our audience that is here today, can you tell us a bit about what is the Center for Functional Nanomaterials? What is its mission and what kind of research goes on at the CFN?
Yeah, so we are what's called a user facility that houses a lot of scientific equipment that allows us to both make and study nanomaterials. And I get to help scientists from all around the world and the United States come and use our facilities, use the tools that we have to perform all kinds of experiments. We don't just buy equipment, we're also known for innovating. So sometimes we want to measure something about a nanomaterial, but the tool to measure it doesn't exist. So we also tweak and develop new capabilities. We're a free resource to the scientific community. So anybody can write a proposed experiment and it gets evaluated and scored. And then depending on how much experiment time we have available, we allow you to come and use our tools and interact with all of the scientists here to really make your experiment a success.
And for the folks that might be interested, it's free, right? If you ask, those tools are accessible to scientists of anywhere, free of charge, as long as you publish, correct?
Yeah, absolutely. And of course, we don't expect you to know how to use the tools. We help you perform the experiment. We give you guidance on what's possible.
Can you share a little bit about what kind of science goes on at the CFN?
Yeah, we have people working on developing new materials for quantum computing. So quantum information science is a really hot topic these days. New catalysts for fuels production, fuels for transportation, understanding how batteries work and why they fail. Also using DNA and other kinds of biomolecules to help arrange nanomaterials in new and exciting ways. And this could be used for therapeutics, drug delivery, things like that. And then also I have a colleague working on trapping xenon and argon, which are really rare gases and happen around nuclear reactions.
Oh, that's a very cool one. Very, very nice. And so when I first introduced you, I mentioned that you are a staff scientist. So what do you do at the CFL? What is your role in the department, in the group?
Yeah, so half my time I help users come and do experiments, and then half my time I spend doing my own scientific research. And the equipment that I uses X-rays and infrared light to monitor chemical reactions of nanomaterials. So it's often advantageous to watch a chemical reaction while it's happening instead of looking at say a catalyst before a reaction and after a reaction. It can be very different during a chemical process. So I specialize in watching the chemical reactions.
As it happens, right?
As it
happens. That's very cool. So before we even get to some of the sharing a little bit about what you do, for the audience here, can you just let's just give a little bit of sense of what the scale we're talking about when we think about nano. So what is nano? I know you have a few slides to share with us.
So I have a couple of slides to talk about how big is a nanometer. So we can think of it as 1 billion times smaller than us, 1 million times smaller than the head of a pin, one of these safety pins, 100,000 times thinner than the edge of a knife, 10,000 times smaller than a little piece of baby powder. And then bacteria, maybe you've seen in a microscope, chop that up 1,000 times, you get a nanometer. And then my favorite statistic is our fingernails grow a nanometer a second. So nanometer, nanometer, nanometer.
That's pretty cool.
Yeah. And then why do we even care about things on the nanometer scale, right? So if you think about human history, there's been all of these like ages, we call them. So the Stone Age focused on how we were able to use rocks and make tools. Then we learned how to deal with bronze, then iron, and now we have silicon for our computers, plastics, steel, all of these things, help us in our cars and our phones and computers. So then the US is wondering what's the next material of the 21st century. And we're betting that it's going to be nanomaterials. And this is particularly relevant because as we sort of hit the end of our computing power with silicon-based computers, we need to move to quantum computers. And that happens on the nanometer scale. So I think we're making a wise choice in the types of materials in science.
You also mentioned that some of the innovation, some of the ideas that comes into the development of this this nanomaterials, the nanomaterials comes from nature, right? It's something that you and we were sharing a little bit about that. Can you give us a little bit of a few examples of that?
Yeah. So one of my, forget about this slide.
Go ahead.
Yeah. So another reason why the nanoscale is important is you can have the same material in different forms and they have very different properties. So for example, coal is a type of carbon and we can burn it and get energy. But if it's in the form of graphite, carbon is actually really soft and we can write with it. But if it's in the form of diamond, that's still carbon, same stuff in coal and graphite, but just the way the carbon atoms are arranged, it's really strong. And then a nanomaterial called graphene is just one atomic layer of carbon atoms. And that's super strong like diamond, but we can't make large, gigantic sheets of graphene yet, which is why we need lots of science into learning how to control things at the nanometer scale. And nature actually has done this, as you mentioned, a little bit. So I always like it when my colleagues and I take inspiration from nature. So some of my colleagues have noticed that on a moth eye, there's this dotted pattern, and they were able to reproduce that pattern on a piece of silicon. And you can see in the bottom picture that one of these pieces of silicon is a mirror, which is how silicon normally is. And then the other has this coating that's a pattern reproduced from a moth eye that makes it less reflective. And this is actually really useful for solar cells, because you don't want your solar cell to reflect the sunlight. You want it to absorb it and make electricity. So this is an example of using a pattern found in nature on the nanoscale to improve some of the technology that we have.
Actually, very nice. So have this been able to be tested at the laboratory? Let's say we have other facilities and solar panels to see how good it is in conversion, or we're not there yet?
I think they've made test solar cells, and I believe they were working on a patent in order to make it widely available and apply it to lots of different things. You could think windows, maybe.
Yeah.
You could put this coating and not have a reflection.
Very cool. Very nice. So now that we have a sense of, we understand the scale that we're talking about. Actually, now, can you tell us a little bit about the work that you do? I know you work in the catalysis group at the CFN. So can you tell us a little bit about, just to bring the audience kind of to the same level, what is catalysis? What is it that you're studying or looking for?
Yeah, so catalysts are around every day in society. So you have one on your car, the catalytic converter. And it's a material that helps a chemical reaction go, but isn't used up. So your catalytic reactor lasts for a decade or longer, right? Because it's always there, it doesn't get used up. But what it does do is takes gases like NOx that are sort of irritating when we breathe them in and is air pollution. It takes that and it converts it to something that's a little more benign and is less toxic for the environment and for humans. So in that case, it's just always there and just helps chemical reactions work a little bit better.
So in the project that you do, how do you apply, what is the application on those catalysts in your research? How do you apply them or use them?
Yeah, so I have one research project looking at gas masks that the military wears. So they were developed around World War I and World War II to absorb chlorine gas and mustard gas. So these have a lot of sulfur and chlorine in them. And so the idea is the catalyst would absorb these toxic molecules and then convert them to something less toxic and then be available to absorb even more, right? So that's a catalyst, it's not getting used up. So you might have heard, unfortunately, in the news, there's other kinds of nerve agents and nasty chemicals that people are using in warfare, such as sarin, VX, soman. And these have phosphorus in them, which is a little bit of a different chemistry than chlorine and mustard, where the gas masks were originally developed. So the formula for the gas masks haven't changed, and it's something like this. So it's just carbon, and inside this porous carbon is metal oxides, such as copper oxide, a little bit of metallic silver, some molybdenum oxide. And so what I was studying is how these phosphorus nerve agents bind to the metal oxides. And if they're catalytically decomposes these nerve agents, or if they stay around, things like that, how are they absorbing it? But I didn't use the real nerve agent. I don't want to go near that stuff. We use something that's kind of like the nerve agent, but less toxic. Same kind of chemistry.
So when they bind to the catalyst, the chemical reaction occurs. So then you have this nerve reagent that is that is toxic, of course, becomes something less harmful.
Right. So I was looking at, is it trapped or does it react and become something less harmful? Okay. And then another thing I was investigating is, I mentioned air pollution before. Mm-hmm. So people haven't really looked at, if you're wearing your gas mask in a city, is NOx air pollution going to come into your gas mask and change the chemistry? Maybe it gets absorbed also. Mm-hmm. So then there's less room for the toxic stuff to be absorbed if the need occurs, things like that.
So if I hear you're looking to see if, in case of air pollution, it can affect the efficacy, how that mask functions to do the job. Is that
exactly? Yeah. Is it still effective in air pollution? We all know that masks are humid environments now, right? So how does mm-hmm. humidity affect it? If you're filling up your Humvee and you're around diesel fuel fumes, I investigated how those kind of fumes affect the absorption in the masks, things like this.
That's a very cool, because in school you always talk about catalysts in a very different use, right? And so cars and so forth. So to kind of have something like mask, which I never thought about, that's an application. It's actually to me quite fascinating. And now that we're the topic of mask, and the topic of one thing that you were mentioning to me, you and I were talking about, that you were also looking into how steam, right, or dry heat and affects it has a cleaning effect on masks. And one of the things that you were looking at was also in terms of the N95 mask, right? How these ways that we have to clean other products, how that affects mask function. Can you tell the audience a little bit about what were you doing? What would you work on that area?
I can show you one of my masks. So at the beginning of the pandemic, there was a shortage of N95 masks, and we had to figure out how can we make them last longer. And so there was a group with researchers at Stony Brook University and other departments here at BNL looking into, as you say, comparing steam cleaning versus just heating it dry without a lot of water around. And how does that affect the structure of the mask? And this is one reason I like working at the Center for Functional Nanomaterials, is because these masks are made out of plastic fibers, polymers, and I don't really know a lot about that science, but I do know how to measure them with X-rays and infrared light. So they came to me asking, can you help us figure out how the surface chemistry of the polymer fibers is changing based on these two different treatments? And they used equipment, my X-ray equipment, and then also some imaging to look at the fibers. And they found out that steam cleaning with the water causes more fiber breakage, and sort of implies that, hey, maybe we need to look at how long can we actually use these masks for, how many times can they be cleaned.
And what did you find? Was there any difference? So if the steam has a greater damage to the fiber, for how long can you use a mask that was steam clean versus dry heat?
Right. So I don't think they looked at the number of times they could actually go through and use it, but they did see that there was more fiber breakage by just having water around. So water was starting to stick to the surface. It could be reacting with the surface fibers, causing, the fibers to break a little bit more easily. And over time, this is could really affect the performance.
Very, very cool. And Tri, that was one of the big questions during the early, like you said, during the early pandemic, when there was shortage of masks, and so how it was relevant, very important for the healthcare workers, facing patients at that time. Very, very cool. One of the things that you and I talked about is that you have you do a lot of quite interesting broad science. We talk about masks, gas masks, and N95 masks, but you also have work going on related to biofuels, looking to see whether enzymes, catalysts, right? Enzymes that used for biofuel processes, that potentially used for biofuel processes, can be used on paper.
Yeah, so I have another collaboration with a user who comes to do measurements on my X-ray equipment. And she is interested in converting lignin into fuels for transportation. And so you see this huge chemistry molecule. It might be a lot of chemistry for some of you. I'm a chemist and it's a lot of chemistry for me. You know, that's the point, right? We want to chop that molecule up and we want to take out all of that oxygen and convert it into something that's more familiar, like octane. I'm sure you all know about octane when you fill up your cars, right? So the point is you're taking lignin, this gigantic molecule, and converting it into something more simple, octane we can put in the car. And interestingly, lignin comes from, it's a byproduct of paper manufacturing. It's a part of the tree that you can't use in the paper. And it's this tarry looking black goo, I guess. And then once it goes through processing with a catalyst, then it becomes this colorless biofuel that you can, you know, fuel up your car with. And so if I stop sharing, I can show you the catalyst that we have. So people always talk about catalysts in the industry. It really just looks like, we were talking, it looks kind of like nerds, like the candy. So it's actually just sort of like porous sand. So it's made of silica, same thing as sand. And inside are just some metals, nickel and molybdenum. And so we know that the nickel helps the molybdenum chop up that gigantic molecule, but we aren't really sure how and what effect it actually has. And we can make it better and more efficient if we could figure out what it was doing.
That's very cool, you know. And for folks that, you know, the lignin is part of the cell wall of that part of the structure of the plant. So it's that very, you know, a good way to generate, you know, utilize, make biofuels, right? Without consuming some of their food, you know, not some of the resources, some of the, you know, potatoes and corn, things like that, that's also part of the food line. But the thing is, for me, it's also another way to use our waste, you know, that we generate in a very useful, purpose way.
Right. So I mean, you're cutting down the tree anyway, right? So you want to use all of it that you can.
All of it.
And if we can figure out how the catalyst is working, and we can make it more efficient, then that also makes it more sustainable. You need less energy to produce even more fuel from the same tree.
Now I have a question. The catalyst that is used for this purpose is not the same enzyme that is used in other processes, let's say other material that is not dead.
So it's actually used in fossil fuels processing also. And it's my understanding that my collaborator was like, oh, this works for similar processing of fossil fuels. So let's try it out on this biofuels manufacturing. And it turns out it works, which is a great start, right? But then the question is, how do we make it better? And when you're processing tens of thousands, hundreds of thousands of gallons of lignin, you know, every percentage in efficiency matters. So we want to make it as best as it can be.
Very cool. Very cool. So if you have any questions, you're welcome to put it on the Q&A. We'll be glad to you know, actually we'll be glad to answer them. Now we're going to pivot to your career path. So one of the first things I'm going to ask is, what got you hooked into science?
Yeah, so we were talking about this earlier, a couple of things. So I remember taking a field trip, I think in the 8th grade, to Greenbrier Telescope in West Virginia. And it was, I think it does radio waves. And two things happened. I saw liquid nitrogen for the first time, which if you don't know, liquid nitrogen is super, super cold. And then you pour it and it evaporates immediately and makes instantaneous fog. And it was just so much fun to watch. And then also I saw a picture of the moon, but it didn't look like the moon. It wasn't an optical image. And I didn't understand at the time, and I still don't. I think it was radio waves, right? But what I thought was amazing is that a scientist could take a a picture of the moon in a different way that I see it and learn something. And I just found that fascinating.
And that was the beginning, right? To
Yeah.
that path, to that path. And so from that first experience, did that, you know, those experiences that you just shared with us, that take you to the path to where you are now? So what was that journey? How do you end up to where you are now?
Yeah, so I didn't end up in astronomy, but I was hooked on math and science. I still like astronomy. But my older brother told me he worked in an aluminum factory making aluminum foil and aluminum pipes. And he said, we always need more chemical engineers. You should do that. And I thought, oh, okay, sure. But then I took chemistry classes before I got to the engineering and thought, wow, this is a lot of fun. Again, the interesting value of just, you know, all the pretty glassware that you can imagine that Hollywood does a good job of portraying. And chemical reactions and color changes, I thought was just fascinating, and understanding the reasons why those happen. And then, so I got my bachelor's degree in chemistry with a math minor because I still love doing math. And that was from James Madison University in my hometown in Virginia. And then I was exhausted because I was putting myself through college. So I was working at an herb factory, packaging those little plastic bins of like parsley and basil and stuff. So I still to this day don't really like pesto, but it put me through college. So I was tired, and I got a job in a quality control lab and a dairy factory making Nesquik milk and HP Hood lactose-free milk and coffee creamer. And so I would test the pH and the total organic solids, test to make sure there wasn't bacteria everywhere. And it was really interesting. But I knew it wasn't for me because I like investigating problems. So I applied to graduate school and went to the University of Arizona, which is very far away from Virginia, but it was a lot of fun. And that's where I started doing work with X-rays and UV light to investigate molecules. Then after I got my PhD, I took a break again. And you gotta understand when you need a break, you know? So I taught general chemistry lab courses at a community college for about a year, and then accepted what's called a postdoc position. So basically you just do research and work on a science problem. And I went to Lund University in Sweden. And that's where I really learned how to use X-rays to investigate chemical reactions. And it was a blast living in Europe, but I wanted to come back to the States. So I took a second postdoc position at Lawrence Berkeley National Lab, just outside of San Francisco in Berkeley, California. And I worked there for 2 or 3 years, doing the same kind of thing, the X-ray spectroscopy, you know, so I was learning how to do the spectroscopy and the science from the best people in the world. And then I came to Brookhaven National Lab in 2018.
Very cool. So I like that you mentioned that, you know, you take breaks, and not everybody follows a very linear path in this process. So it's a marathon. When you decide to start this path, it's really a marathon. So taking the time to kind of pause and see where your next step will be is a very important for the success.
Yeah.
For the success of that journey. Did you do any internships when you were in college, or in college? I'm not sure in high school were available to you, but in college, did you do any internship? What was the impact of those experiences?
Yeah, actually, this was maybe another pivotal step in my science career. Another deep memory. I did. It's called an REU, Research Experience for Undergraduates. So a lot of universities have them, and you work for a summer. I did one at James Madison University where I was studying, and it was a lot of fun, and I learned the research process. But when I actually went away from that university, I went to a university in Idaho and I'm not going to remember which one it is. It might have been the University of Idaho, but I just lived there because they had a joint one. And I actually worked at Washington State University because it's right on the border of the two states. And so there I got to see what a graduate program was like. I got to see what does it mean to take science to the next level and have access to some more tools. There's also Pacific Northwest National Lab, another DOE lab. We took a field trip there where I saw my first gigantic piece of equipment wrapped in aluminum foil, and I heard terms like Auger electron, you know. So it's these little teasers in science that have just hooked me along the way. And so I've always sort of kept my eye out for national labs, thinking this great science goes on there. How can I get in on that?
I know earlier you mentioned how impactful those internships are, right? Before it's making the connections and learning what is it that goes on, right? And making the networking that you get to make on that. So, you know, the REUs are one way. The Department of Energy had the science on the graduate laboratory internships that allows you to go and you know, do this kind of experiences at the national labs, which actually said are very cool and important to do it. To be part of.
I was going to say I've mentored 2 undergraduates, so I like to.
That was one of the questions.
Yeah, so I had one student before the pandemic. She came and worked on a little project with me, and then she is now in graduate school. And then another student who worked with me last summer, who's applying to graduate schools now. He worked with me remotely, but he was really interested in quantum information science. And here's the value of your network. I don't know much about quantum information science, but I know people who do. So I was able to say to my colleague, hey, I have this intern. Do you want to work with him and me this fall? And he can get some experience learning more about quantum information science from you that I can't give him, you know. And so he used that to his advantage, and now he's applying, and I think it was accepted to a quantum information science program at a university. So
very good. You're right. It's the connections that you just said, the connections that you make. Very good. So that was one of the questions. Did you take the departments? Did you take interest in your department? And the answer to that is yes.
Yes, we do.
There's a question in the chat asking, what are some classes that you would recommend undergraduates to take?
What classes?
What are some classes, courses that you would recommend an undergraduate to take?
Yeah, take what you find fun, I guess. So I really enjoyed math. I wanted a math minor. I thought about doing, you know, a math, a second degree, but I didn't put in the full effort for that. But I did more than a minor just because I liked the classes and I wanted to learn about, I took a class in logic or whatever. I learned some French, so I wanted to keep up with my French skills, so I took some French. But basically, whatever science you might think you like, you should take that. I personally am not into researching biochemistry. I think it's very important, but I mean, it's just not for me. So I took minimal biochemistry, right? I enjoyed physics, so I took extra physics. I mean, it's really important to take the stuff that you have to take, of course, but then what interests you. And it's also fun going a little bit outside your taking things for fun or things that just sort of vaguely interest you, because my French turned out to be very helpful when I was living in Sweden, just because I would go to the French synchrotron. And so you have to find your way around in France to get there. So I would go to a lab in France to do experiments. So yeah, these extra classes that I enjoyed helped.
That's a great advice, because it gives you a broader sense, right? A broad exposure to, and then you can decide it's what really, it helps make, at least for me, will help make the decision to which areas I might be interested in pursuing later on. It's a very good advice. There's a question in the chat: do you consider having fundamentals of coding important? Basically, is it coding important to do these days or to take these days?
It is. And it's
Should I
becoming
take
more and more
coding? That's the
important.
question.
So I took a Fortran class in my undergraduate.
Really?
I don't know if people know what Fortran is anymore, but apparently scientists and mathematicians still use it, but I don't know if that's true. But what it did teach me is, I mean, a lot of programming languages I found have routines and they have subroutines, and you're just sort of changing how you call all of those. And while I have not used Fortran, I've used sort of the programming logic in my data analysis and in programming instrumentation, things like that. So that is helpful. Another thing that I wish I had done is graphics, some sort of graphic arts class, because I need to make pictures and I need to make presentations, and I make figures in PowerPoint and I know they look terrible, but I don't know how to make them better. So I wish I had a basic understanding of some graphic software.
There is Anne Salazar mentioned that she took Fortran as an undergrad. Yes, it's an old language, and you're right. A lot of mathematicians folks are still, doing using Fortran. Yeah, and I think now with computer science cross-cutting among various disciplines in STEM, is something that I think is something that I think students should at least to be informed.
Absolutely.
Have some sort of experience on it. I agree with you. I wish I had it, and that never happened to me. You mentioned that you mentor students, right? And as part of the SULI program. Okay. So how is important for you? What did you get? So what did you learn? How has that experience enriches you as a scientist, as a researcher? And how important is that experience for the students, for the mentees as well?
Yeah, so students ask really basic questions that just stump me. And I have to go back and learn the basics, and it actually helps my research. Or they just ask, why does that happen? And I just stop them. I don't know. So a fresh set of eyes from an undergraduate intern really just helped me see my science in a new way, and help me with fresh ideas. I mean, you might think, oh, I'm just an undergraduate, I can't possibly add, but I mean, you do. Undergraduates really just see things with fresh eyes, and it really helps. And I've seen undergraduates too. I mean, it elevates their way of thinking about science. They learn more the scientific method. I think as an undergraduate, you maybe think there's always a right answer when, I mean, we don't have the answers. That's why we do science. And so a lot of the interns that I worked with finally understand that like, there's no right way of doing something. There's just, you try and you look at what results you get and can you explain them?
Very, very nice. Very good. There's a question asking, what excites you the most while working?
I really love working with users because they bring me some new problem and I get to do science that I'm maybe not an expert in, but I get to learn a little bit about their science, like the polymers and the face masks. So I get to learn little bit about that. Get to learn a little bit about the biofuels, about catalysis, batteries. So I just absolutely love when a new scientist comes to me saying, I have this problem. Can you help me figure out how to solve it?
Very collaborative.
Yeah. So solving problems and in all different kinds of science.
Sounds like you're never bored.
Nope.
So one of the things that you and I were talking about was in that conversation is that, how valuable the value of an inclusive and diverse work environment it is. So it is important, right? Because we have big problems to solve, and in everybody's point of view, it helps to find solutions to those problems. And so how can we encourage or, encourage young women and students of color, underrepresented minorities as students to pursue a career path, to be participants in the STEM fields?
Yeah, so diversity in any possible parameter you can imagine is so important because it helps people with different ways of seeing a problem have different answers that I wouldn't have. So I really think it's important to have a diverse team, and not just to have them, but include them. And I guess I would say I've been lucky enough that I've always felt included. And I think that's the best way to encourage people, is to make them feel included. I never felt like I couldn't do something. I mean, maybe I did, but I had a support system saying, no, you can do this. Because science isn't always easy. The classes can be hard, but if you have a support team saying, calm down, it's okay, you can do this, they get you through it, then it makes you feel like you can achieve it. You can get over whatever test you just took. You can get over somebody broke your temperature reading and you have to take it apart and fix it. I mean, and I don't think that's just science. I mean, that's everyday life, right? There are all these challenges. And so having a support system is extra important, I think.
That's a very important, and I'm glad you said it. You know, science, STEM studies are not easy. So they're not. It's not the way to put it. But having a support system and a support group that can lift you up when things are challenging and you feel like I'm not cut off for this, and yes, you are. It just that time that way will pass, and you will rise. You know, you will rise above that wave. So that's a very great advice, actually. Advice. So let me ask you, perhaps as we are approaching very close to our time here, if our audience today did not remember anything that you say, anything, and you know that could happen. So anything that you said, what 3 things you want to let them know, that to, you know, what kind of advice, 3 pieces of advice that you want them to remember?
Yeah, so always have your support structure, like we talked about. Have people who got your back. It's important. Always know yourself, right? So I took breaks from my career because I knew I needed it. And my last piece of advice would be always be flexible. I sort of took opportunities as they came. I kind of had a general idea about what I wanted to do in my career, but I was flexible. That allowed me to take the breaks that I need, and opened up a lot of opportunities at great places.
Very good advice. Be flexible. That's an excellent advice.
Yeah.
Be flexible and take any opportunity that comes to you, no matter how big or small that is.
Yep.
All right. Thank you, Ashley. Thank you so very much for being our guest today. It was a fun conversation. I learned I learned something about, now looking math in a very different way, particularly the gas mask. And so I thank you so much for your time. We appreciate the sharing all that information with us. So please, our next Science Thursday will come on April 28th, which is right after spring break. And so looking forward to see you all at 4 p.m. We like to thank Brookhaven National Lab for hosting this event today. And then we encourage you to check our programs, our programs, research programs and internship opportunities at the Office of Educational Programs. Sal will drop the link to the OEP page on the chat if you're interested in searching what we do, and follow us on social media. Thank you so very much, everybody. Have a wonderful day. Enjoy your evening, and see you next time. Bye-bye.